we now have a quite good understanding how to use semi-manifold reduction or multiple scales analysis to reduce the dynamics of a large system. We thought of ODE so far, to just a single equation for either a steady bifurcation or for a Hopf bifurcation. So in those cases, we had a single real eigenvalue going through 0, or we had a complex pair of eigenvalues crossing an imaginary axis. So in the first case, we had a one-dimensional center manifold, and in the second case, we had a two-dimensional center manifold on which the oscillations occur. Now, in general, you could also have multiple real eigenvalues going through 0 at the same time. Well, in that case, the dimension of the center manifold would be just as large as the number of 0 eigenvalues you have at that bifurcation point. And that could lead to interesting phenomena, because even on that slow center manifold, you could then have interaction between these modes, which can lead to non-trivial behavior. And so we want to look at that in some detail. A very natural way where things like that could occur is if you have a symmetry in the system that forces that multiple eigenvalues cross the imaginary axis at the same time. When I say at the same time, meaning for the same control parameter. So for instance, if you think of Rayleigh-Bénard convection, so we have this fluid layer, which is heated from below and cooled from above. And so imagine you have like a square box now. So this imagine this is like a square box, and so is this. So in these situations, you could imagine that either you have convection like this, the way we drew it before. So we have like convection rolls like that. And if you had the top view, this would mean that you would have stripe patterns oriented like this. But because this box is square and therefore has symmetries, as in you can rotate by 90 degrees, you can reflect about some axes, you could also have actually convection that looks like that, right? So that the stripe pattern would actually be oriented like this. And because of the symmetry, both patterns would be equivalent. And so, of course, the eigenvalue characterizing the instability would have to cross the imaginary axis for the same control parameter. And so then you have multiple modes, and you have a higher dimensional center manifold. So we want to look at that, but before we can do that, we first need to see how we actually get from a PDE to a low dimensional center manifold in the first place. So that's what we're going to do right now. So we'll take a simple PDE model, excuse me, and we derive the amplitude equation from that PDE. We'll use a center manifold approach, but you could also use a multiple scale approach. Okay, so the model we want to do is the following. There are some quantity psi, and it evolves according to this PDE. There's some control parameter R, and then there is a derivative term, which looks like this. So there is a fourth derivative and a second derivative. And we'll see what that does in a second. And then we have a nonlinear term. Let's just, for simplicity, just take a single nonlinear term, but let's make it a gradient actually, which has its significance later. Okay, so that's a nonlinear PDE and hard to solve. But obviously there's a simple solution, psi equals 0, which exists for any kind of value of R. And so our standard strategy is we expand around that solution, look for instabilities, and then take it from there. So let's do a linearization around that point. So when we get ansatz psi is equal to, okay, well, this is a PDE, right? So it's a constant coefficient PDE. So we can make a Fourier ansatz, right? So let's make a Fourier ansatz e to the IQx, where q is some wave number. And we want to know whether that actually grows or decays. So we put down a growth rate. And in principle, I guess there would be some amplitude, but I don't need that for the linear stability. Okay, so when I plugged it in, I get for the growth rate, I get simply sigma is equal to R minus 1 minus Q squared, quantity squared. So I can sketch that. So I'm going to sketch as a function of Q those values of R for which the growth rate vanishes. And it's easy to see that this looks like the following. There's some minimum here, which actually happens to be at 0. I mean, R equals 0. And then the function looks like this. And the statement is that we have, when R is bigger than this number, then the growth rate is positive. So that means actually that the basic state is unstable, whereas below the curve it's stable. Let me say that more precisely. When it says unstable, it means if you were to pick this wave number here and apply a perturbation e to the IQX with that wave number, then if R is above the blue line, that mode would grow. Now in that large system, let's imagine we have, well, actually there are different possibilities we could consider. We could consider a very large system. We could consider an infinite system. And then this picture is actually what emerges because the wave number Q is arbitrary, right? It's a continuous variable. So we actually assume the system is infinitely large. If the system was finite, let's assume periodic boundary conditions. And then, of course, in that finite system, the wave number would be limited to a multiple of 2 pi over L. Let's not ponder that further here. Let's actually assume we're in an infinite system. So that means in an infinite system, these modes here, if the R value is here, all these modes would destabilize the basic state, whereas these modes would not. So obviously, if you now were to change the control parameter, if you start with negative values, as you increase the control parameter, the mode that kicks in first would be here at Q equals 1. So in the following, we'll just assume we'll take a wave number close to here. You might as well think of Q equals 1. I'll just keep Q there still as a marker, but you might as well think of Q equals 1 if you want to. Then we want to see what happens with if we expand in these kind of modes and how we get an amplitude equation for that. Okay, so well, let's make an ansatz as always. So the ansatz will be our psi. Oh, I need more space. This is gonna, the calculation is a little bit lengthy, but okay, so psi will be equal to some amplitude A, which will depend on time, and that's that time evolution we're looking for. I'm not gonna write down A of t, I'll just write A times e to the IQX. So that is the mode that I imagine is destabilizing. Then because we have nonlinearities, there is a mode B with twice the wave number. Then there could also be a mode C with wave number 0. And there could be a node D with e to the 3 IQX, and so on. And of course, also a complex conjugate. So we need to plug that into our equation. So psi goes in here. And the most important part here is this nonlinear term. And so we need to figure out what this generates. And so let me write out actually the derivative first, so we just have an easier time to just see what the nonlinear terms look like. So we have the d psi by dx is given by IQ A e to the IQX plus 2IQ B e to the IQX times 2 plus 0 times C plus 3IQX, 3IQ D e to the 3IQX plus higher orders plus complex conjugate. So that would be actually minus IQ A star e to the minus IQX and so on. Okay, so what are we going to do? We're going to plug this in, and essentially we're doing a Fourier expansion, right? So we just sort now by Fourier modes, and we focus on, start with the Fourier mode Q, and then we look at the other modes. So let's see what happens. Okay, so let me write down. So we have a mode e to the IQX. So what does that equation look like? We will have a dA by dt equals, and then we have an R, and then whatever this does with the wave number. So that combines to something that's R minus, and then we have 1 minus Q squared times A. And then we have nonlinear terms from the term here. And so now we need to see which of those nonlinear terms generate a wave number IQX. And so we see if we combine A, no, I have to point here, A and A star, that of course gives a wave number 0. That's not contributing. So what we can get for A e to the iqx, there's a term a squared. Okay, let's write that down. So a squared means that we take from the d psi by dx, we need to square that. So you may have to imagine this thing here twice. And so for the a squared, I get a from the first factor and a from the second factor. I get one of those. So I get here a minus q squared, a squared. No, that would be true if I was going for 2qx, but I'm not. I slipped. Let me take that away. I'm looking just for e to the iqx, right? So I have e to the iqx, I can have a b and an a star from the other factor. And I can have this a star and a b from the other factor. So I get 2 times 2q squared times b a star. What can I have also? I could have c with a, but the c doesn't show up, right? So therefore I can, maybe just for completeness, I'm going to write it down, but there's also plus 0 times a c. And then we have also the possibility of having d with b star, right? That also gives it 1. So I have minus, and there's again 2 of those. So I have 12q squared d b star. And then of course higher order terms. Good. Let's think about this problem before we write more, because it can easily get out of hand with writing. So what do we have in mind? We have in mind that our mode A is a wave number right here, very close to here. So then means the mode B is at twice that wave number, which is about here, which clearly has a negative growth rate because it's below the neutral curve. I should actually have called that thing the neutral curve. This curve here is called the neutral curve because the growth is neutral on that curve. Okay. So B is somewhere here and is damped. C is here, which is also damped, and D is even further out and is also damped. So in short, if we're really in this regime here, the only mode that's actually growing is A. So in our center manifold approach, we're looking for parameter value for one mode has a growth rate of 0. So we have a center eigenspace. And then we want to have the rest of the modes being in the stable eigenspace. So in our case, we have A forms the center eigenspace, and all the other modes are in the stable eigenspace. And so in the center manifold approach, then, what we want is we want to have that center manifold, which is a one-dimensional manifold in this case, because we have, well, it's not quite true because we have A and A star, but okay, but it's a center manifold which is parameterized by A, and B and C and D, they're all following the A. So the A is our coordinate on that center manifold. And B, C, and D are given by nonlinear functions of that coordinate A. Right? So we know the center manifold is tangential to the center eigenspace, and therefore this function B of A is strictly nonlinear. So that means that if you look at the terms, this B here is strictly nonlinear in A, so at the very least it's A squared. So this would be a cubic term in A. Well, this term we can ignore. dB, each of these is at least quadratic in A. So this would be a quartic term and would be higher order. So far we read that the equation for A that we eventually get will only have a nonlinear term from this BA star. So we only need to worry about B, and to leading order, we only need to worry about B in terms of order A squared. Good. There's one more thing we need to do. Right now, we are talking as if we were exactly at the bifurcation point, but we want to be able to change our control parameter slightly above. So again, we need to look at the suspended system where the control parameter becomes a dynamical variable and the center manifold is increased by that one dimension. And so therefore, we also have to worry about the transformation that gives us A in terms of, B in terms of A. It will also have to depend on mu or whatever our control parameter is. Okay, so let's write that down. So this is going to be the growth rate of A. So let me call that actually mu. And so therefore now we can describe our center manifold, which is this manifold in this space of A, B, D, C, A, B, C, D, and so on. So there we have B is a function, let me call it HB, of A and A star. And because we're doing the suspended system, it will also depend on mu. But it's, as I said, it's strictly nonlinear in these quantities. Okay, in principle, we would also have to have an H for C and an H for D, but as we just found out, to leading order, we really don't need C or D, so this is going to be all what we need. Okay, so off we go, I guess. So we do our Taylor expansion, and well, let's do it. So HB, we expand as, well, it has to be quadratic in its arguments. So there's a term alpha B times A squared. Then there's a term beta B times A absolute value squared, gamma B times A star squared, plus now come more terms because we have to have the mu. So there's a delta B mu squared and a rho B times mu A and a tau B like times a mu A star, and of course higher order terms. Okay, so this is kind of messy. So let's think about what we need. The strategy is that there is an evolution equation for B, right? There's an evolution equation for B, which we haven't written down yet. But that evolution equation for B has sort of two origins in some sense. On the one hand, if you do your Fourier expansion here the way we did it, and we'll do that in a second, then there's an equation dB by dt equals something. But at the same time, because B is simply given by H, the evolution equation for B is also emerging from chain rule on this guy. And setting those equal will again lead to our conditions on H, right? So we need to write down the equation, evolution equation for B in both versions, so to speak. So on the one hand, we have dB by dt. So maybe I'll write it down like that. So we have dB by dt equals, by chain rule, we have dHB by dt times, no, that's wrong, dHB by dA times dA by dt plus dHB by dA star by dt. And then comes in principle also dH by d mu, because the mu is sitting here. But that will be multiplied by d mu by dt. And mu is constant, right? So we just have this formal thing of having the phase space extended to include mu, but mu doesn't change. So we don't need to keep that term at all. So this is simply now whatever dB by dt is if we do our Fourier analysis of the original equation, right? So we need to see in this equation, what are the terms that have an e to the 2 iqx? So let's write those out. So we get first, oh, I should scroll back. So we get first, from this linear term, we get something with b, which looks just like the one for a, except instead of 1 minus q squared, we have 1 minus 2q quantity squared. And then we have the quadratic term. Okay, so let's write that down. We have here an r times b minus 1 minus 4q squared times b. That's the linear part. And then we have, from the derivative here, where do we get e to the 2iqx? That we get if we pick a squared, well, times iq. So that's minus q squared a squared. That's a term. Minus q squared a squared. And then what else can we have? 2qx. It could be, of course, a d times an a star. But that's higher order, right? Because d is at least quadratic, times a would make this at least cubic. But the term we've written down right now is just quadratic. So we don't need that term. Similarly, of course, we could have, well, b times c is not going to do anything. And so that's actually the only term to quadratic order, right? Maybe you should say plus higher order terms, but it's the only one that comes within quadratic order. So that's it. So what is it? The unknowns are these coefficients, alpha, beta, gamma, and so on. We need to pick them such that this equation is satisfied. Let's look. So right now, the lowest order term that we see is this quadratic a square term. Let's look at the left-hand side. Here's an a, but the a by dt, what is that? That is actually the a by dt was our equation, is mu times a, right, which is quadratic, or it's b times a star, which is cubic. So dA by dt is therefore quadratic, mu times a, and times dh by db, dhb by dA. H is quadratic, derivative being a makes it linear. So we have quadratic times linear is a cubic term. And this is also a cubic term. So actually to leading order, the only things we have is this term and then whatever b offers. B is quadratic, yes, so we can balance things. And so what we see among the many coefficients that we have in H, the only one we need is the alpha, because there's only this term a squared. Okay, so therefore we need to balance pick alpha so that we solve that equation. And when you do that, you get alpha b is equal to 1 over 1 minus q squared quantity squared minus 1 minus 4q squared quantity squared. And b is equal to simply this alpha b times a squared. Okay. That was then not so painful, because now we're actually done, because the equation for a, what does that look like now? Well, it has this term mu a, and then we have b times a star, but we now have b is sitting right there. So this gives the term a squared times a star, which is a absolute value squared times a. And so let me write down the final answer. Let me assume for simplicity that we're really at the minimum. So we are at q equals 1. And in that case, we get dA by dt is equal to mu a minus 4/9 a absolute value squared a. Okay. We've derived a nice little ODE that describes what happens in this PDE when you increase the control parameter just a little bit about r equals 0. And you're looking at modes q equals 1. So strictly speaking, that would be, for instance, if you just took a box of size 2 pi, and then the wave number would be 1. And in that box, this is what you would see. And as mu is increasing, you get now a mode A, and of course B following, and C and D also following. Good, so let's look at that equation, see what properties it has, because it actually looks quite familiar. It has exactly the same form as what we had for half bifurcation, right? So let's make a couple of notes. The form as that for a half bifurcation. So you of course can say, well, that's sort of odd because this has nothing to do with oscillations. This is a steady bifurcation. You just have the pattern is stationary in time. So what does it have to do with a half bifurcation? Well, we'll get to that in a moment, but let's just sort of note it and see what follows from it, because we know how to solve that equation. We can simply, if you look at the magnitude of A, so let's just say A is equal to R times e to the I phi with some phase phi, then you read off that R satisfies the equation dr by dt equals mu R minus 4/9 R cubed. And that is simply describing a supercritical not half, a supercritical pitchfork. So this pattern arises in a pitchfork bifurcation, which happens to be supercritical in this case. That's because we have minus 4/9. Okay, and we see that the phase phi is actually arbitrary. We have this phase shift symmetry. Where if we shift phi by an arbitrary amount, you still have a solution. And that is also, I mean, of course it has to be just like in half bifurcation because this is the same equation, right? So let's see where that comes from. So recall, in the half bifurcation, we argued, or we saw that the phase shift symmetry was related to a time translation symmetry. And so that suggests that, well, maybe we should think of some kind of a continuous translation symmetry that may induce the same thing here. And in fact, we did assume that our original system was translation invariant, right? We either assumed it was infinitely long or we assume it's periodic, but it's translation invariant. The coefficients are none, they are independent of space. So therefore, we have spatial translation symmetry. And let's see what that does. So if we look at our psi, psi of x plus delta x, what is that? Well, that's A times e to the I q x plus delta x plus A star e to the minus iq x plus delta x plus, of course, higher order terms, which I'm not going to write out. But we see that if we make that shift delta x, it is the same as applying a phase shift to the amplitude A. So that's just like when we did a time translation in the half bifurcation case. So therefore, the equation, since the original equation is equivariant under these shifts in space, the amplitude equation has to be equivariant under phase shifts of this form. So we can say the space translation symmetry induces an action on the amplitude of A going to A e to the I q delta x for arbitrary x, for all delta x. And so therefore, the only nonlinear term that's consistent with that up to cubic order is this term. Quadratic terms are not allowed, and among the cubic terms, only this one is allowed, just like in Hopf bifurcation. Maybe a slight comment, which is not key, but let me mention it anyway. In the Hopf bifurcation, we discussed that when we did the center manifold reduction, we didn't get that equation right away. We got that form of the equation only after a near identity transformation, which got us into this normal form. Whereas in the multiple scale analysis, we got to this equation right away. And so the difference was that this time translation symmetry of the system, the action that comes from it really relied on this exponential factor in time there, right? And when you look at the multiple scale analysis, only the fast time has this periodic dependence. The slow time has general dependence because, after all, we're really aiming for some arbitrary evolution of the amplitude. And so therefore, this symmetry induced by the time translations was really not exact in the sense that it really relied on the separation of the time scales, and therefore only showed up in a normal form and not in the center manifold reduction itself. Now here, we got this equation even though we did just the center manifold, no, I shouldn't say just, we did the center manifold reduction. We assumed, however, that the periodic, the continuous time space translation symmetry is exact, right? We didn't introduce any slow spatial scales. I mean, right now we have no idea why we would do that, but the analogous thing would be to introduce slow spatial scales, and then maybe something like in the Hopf bifurcation would occur. Right now, we assume the solution is strictly periodic in space, and therefore we get this exact form here directly in the center manifold reduction. We would get the same equation we used multiple scales, but let's not talk about that right now. There's one more thing that's actually important. You may have noticed that the coefficient here was actually relatively simple. Well, 4/9, that's whatever that is, but the point is it's only a real number. Remember, in the Hopf bifurcation, this coefficient and that coefficient in general will be complex. Now, it turns out for these steady bifurcations in these space translation symmetric systems, these coefficients have to be real. So this is not a specific feature of this very system. No, this has to be real. And why is that? Well, the original system has an additional symmetry. I didn't expound on that, but this equation here is actually equivariant under space reflections, right? If you have x going to minus x, then this doesn't change, this doesn't change, this doesn't change, this doesn't change. So it's actually invariant under reflections in x. Well, that symmetry will also lead to some conditions on the equation for A. So we need to see what the action of that reflection symmetry is on the amplitude A. And so we can look at that maybe, well, let's look at the original expansion. So if we make a reflection in x, what do we get? X goes to minus x, so this becomes an e to the minus iqx multiplied by A. But we also have an A star term here. X going to minus x makes this an e to the plus iqx. So as a matter of fact, when you compare these two terms, when you go from x to minus x, it's the same thing as going from A to A star and vice versa. So the action of the space reflection, so spatial reflections, let's write that down. Spatial reflections, in this case, x going to minus x induces the action of A going to A star. And so our amplitude equation has to be equivariant under A going to A star. And I think it's very easy to see why that means that the coefficients have to be real, because the equation has to not change or be equivalent if you if A go to A star. So if A goes to A star, the left side, just the whole equation is complex conjugate. This goes complex conjugate, this goes complex conjugate. So when you have A going to A star, the whole equation is just conjugated. But it has to be equal to the original equation, or equivalent to the original equation, more precisely speaking. And so that means these coefficients have to be real. So therefore, we do not really get the half bifurcation equation, but we get an equation like it, but the coefficients have to be real. Okay. So now we have actually figured out how to get from a PDE to a single ODE with the same kind of techniques that we had before. And so now we can address the question, what happens? Well, if we have a two-dimensional system like this, or actually it's three-dimensional, right? It's just the pattern is two-dimensional, where we have a symmetry that these stripes and these stripes appear at the same control parameter. What to do in that case? That's what we're going to do next time.